So good morning, and welcome to this workshop on randomness and learning on networks. Before we have our first talk, I just want to mention a couple of things. Well, first of all, we're very glad to see you all here. Second, this afternoon we have an open problem session. The idea is that people bring their open problems. So if you have a problem that you'd like to share with people, well, maybe you should start thinking about it now. Well, you should still pay attention to David's talk, of course, but to the extent that you can, please start thinking about your problems now so that we have lots of interesting problems to discuss, right? Especially because we have work sessions on the next few days of the workshop, right? So we're supposed to collaborate on problems, so it's important that we have nice things to work on. And third, there's going to be a group picture at some point this afternoon. It was supposed to be tomorrow, but we moved to today because apparently it's going to rain tomorrow and we're going to take the picture outside. So some point after the contributed talks, we're going to be quickly escorted upstairs to take this picture and then come back here. Yeah. And oh yeah, there's a fourth thing, which is there are lots of you who are coming here not just for this workshop, but for the extended period over the next few weeks. And you probably be asked to give a talk at some point during your stay, right? So if you want to preempt me and offer yourself to give a talk, just send me an email or send an email to one of the organizers. We need speakers, so if we don't get enough volunteers, we'll start to bug people. Right? So now, without further ado, I will introduce our first speaker. We're very pleased to have David Gamarnik from MIT here, and he'll be talking about the overlap gap property.
Right. Thank you, Roberto. Oh, maybe you should hold the applause till the end of the talk. You don't know what you're going to see. But thank you, Roberto, and organizers for the invitation. It's a pleasure to be here. Embarrassingly, it's my first time in IMPA, hopefully not the last time, but it's a great time. We took a great hike yesterday with my student friend to Jesus statue, and it was really nice. So now we're going to begin a different kind of hike that we're going to, with a few stops. But whatever we do, I don't have that many slides, and even if I skip some of the slides, that's okay, but feel free to stop and pause and ask me any questions, and I'll be happy to accommodate that. So let's begin. This is going to be a presentation about algorithms for solving various kinds of combinatorial optimization problems. So as we know that most of interesting combinatorial optimization problems are hard, NP hard, so we don't expect to have fast algorithms to solve them. But this is all about worst case instances. So we know that we don't, because P not equal to NP, presumably we don't expect to have an algorithm that solves this problem for all instances. But what if the instances are random? Then it actually changes the story quite a bit, quite dramatically. And in that case, we don't really have a very good and clean picture either of what's algorithmically achievable or versus what's algorithmically hard. And it's, the answer is certainly different from the worst case instances. So for example, the TSP, traveling salesman problem with the random instances, sometimes can be solved to optimality, even though it's an NP-hard problem to approximate up to a huge factor. So random instances create a different challenge, and that's what we want to understand. And this talk will be at a high level about sort of emerging kind of a collection of methods that give a fairly sharp characterization of optimality versus optimality hardness. And to what extent optimization optimal values can be achieved or cannot be achieved, and why, within certain classes of algorithms. One nice thing about optimizing random structures is that often you can predict with high degree of certainty what the optimal value is. And I'll give you a few examples. You know, because of the concentration of the kind that optimal value of this problem is blah, now your goal is to come up with an algorithm that gives you that value or close to this value. And we will see whether we can do that or when we cannot do that and why. There's several survey papers and popular description of these ideas available After the talk, if you're interested, I can give you pointers. So let's get going. Our hike will have 3 stops, and 3 parts, rather. We will begin with the solution space geometry. I will torture you with a little bit of kind of a collection of results that might not be very terribly meaningful, but we will need them for the later part. So we'll talk about the solution space geometry of problems of interest. Then we will state what state-of-the-art algorithms can achieve for the problems. And then we will connect the two and synthesize and see how the solution space geometry and geometry conspires against algorithms of some kind. All right, so that's the structure of the talk. Let's get going. Part 1. So the best way to demonstrate the ideas, I'll give you a couple of examples, a few of them. So let's get to the first example. I hope that at least the models is familiar to majority of you, if not all of you. You've probably seen some version of a random graph at some point of your life. And this is the model that we want to look at first. Before we get to random graphs, let me introduce one object that's probably also familiar to you, many of you. It's called largest independent set problem. Largest independent set is given a graph. It's a collection of nodes that spans no edges. So it's a kind of collection of humans that are not friends with each other. And the challenge is to find the largest incardinality independent set in a given graph. That's a canonical NP-hard problem. But we're going to place it in a random setting, which is the Erdős-Rényi graph. Erdős-Rényi graph, for starting point, it's a dense Erdős-Rényi graph. This is a graph on n nodes where every edge is present or absent with probability 1/2 with equal likelihood independently. This is like the oldest vanilla version of Erdős-Rényi graph, hopefully something you've seen before. OK, so what about this problem of finding the largest independent set? It's actually, we know what it is. With high degree of certainty, with high probability, the answer is very simple and clean. It's twice log n with base 2 up to some smaller order correction. This is a result of Matula in 1970-something. And you can find it in most of the textbooks on random graph theory. So we know what the optimal value is. What about the algorithms? That's in the second part. We'll come to that. Now we're going to ask the following question. What do nearly largest independent set in Erdős-Rényi graph look like? Of course, it's a generic question, so we have to concretize it. What do they look like? We want to study their mutual distances, measured in Hamming distance, for example. So we want to study the overlaps. Are they going to be sort of mostly in one location or spread out in different locations? This is what we want to know. And as it turns out, they look like something like this. There is a threshold which is 1 + 1/√2, so some number is not terribly important, the value. The important thing is that this is less than 2. And at this value, the following thing happens. If you take any 2 independent sets with cardinality larger than this, so this is smaller than optimality, but larger than this, so it's the right scale, then the following is true. You can find, there's 2 numbers, nu1 and nu2, such that the pairwise distances between any 2 such independent sets is either nu1 of this scale. I'm multiplying it by optimal value 2 log n, so that's a natural scaling. Either at most nu1 times the value of the largest optimality, or at least nu2. So it's either small or large, quote unquote. And these numbers you can work out. They exist provided that size of the independent sets is larger than this. And there is an evidence that this is not the case when the size is smaller than that, and that in that case, the pairwise intersections span the entire interval between 0 and 1 upon normalization. OK. This is pictorially what it's sort of how to think about it. It's the same thing as what I said before. Pick 2 independent sets of sufficiently large cardinality above this 1 + 1/√2. Take their intersection. Then you either have this picture, they're going to intersect quite significantly in some sense, or they're going to have a small intersection, but they're not going to have intersection in between. Some range of intersection in between is not going to happen. The proof of this fact is actually not very complicated. It's the first moment argument. That's a canonical way of studying random graphs. Sometimes the only way to study random graphs, unfortunately, but it can be done. So let me pause here, see if you have any questions. Is that all good? And say yes?
What's the definition of your distance?
Distance. We can Hamming distance. We can take as a Hamming distance. So which is, or alternatively, think about the distance as the number of nodes in one set which is not in the other set, and vice versa. So it's a cardinality of the symmetric difference, for example, which is the same as Hamming distance. Good. Other questions, clarifications? Good. All right. So okay, we have that. So what? Now I'm going to extend it in some ways, which is as we extend it progressively, you might find it. You're probably not terribly surprised to see something like this. There's nothing sort of super magical about that. Here's a version of the same fact, which might be somewhat surprising. So in this case, what we're going to do, we're going to look at the ensembles of random graphs. So we have an interpolated sequence of random graphs. I'll explain shortly how this is done. And what we will see is that this property of having high intersection or small intersection actually holds even across the entire collection. All right. So the collection looks like this. I still need to learn how to navigate that. So the collection is built like this. You start with your random graph, G0, the same random graph, and then you set any order of the edges, of the pairs of the nodes, and choose 2 pairs. And then you resample these pairs one by one starting from the original graph. So you have sampled the random graph, then you go to pair 1, and then you resample it with Bernoulli distribution. As a result, you might have, if the edge was there, maybe still there. If edge was there, maybe it was deleted or added, and so on. But it's a random mechanism. Then you do it with edge 2, with pair 2 and pair 3, and then you go all the way until you resampled all edges, and then at the end you get a completely independent graph, clearly, because all pairs were resampled. Okay? And then it turns out, so each new graph is obtained from the old graph by flipping one edge, possibly. And that's important. What's important here is that these graphs kind of evolve in a continuous way. Sort of only one edge changes at a time. That will be crucial for the discussion later on. Turns out that this property I've discussed holds across the whole sequence, meaning the following. So let me give the whole thing here. Now, take any of these graphs in the sequence and take any independent set in this graph larger than this quantity. Same quantity as before. Take any other graph in this sequence, take any other independent set in this new graph larger than this quantity. And then look at their intersection. And lo and behold, this intersection is either at most nu1 or at least nu2. Right? So in other words, this pairwise distance and this gap in the overlaps, and this is why we call the overlap gap property, is that this gap in the overlap survives the entire interpolated sequence of graphs. And that might be somewhat surprising, but it turns out to be true. Furthermore, something else is true, that something else holds, which is as follows, which only applicable to the interpolated sequence of graphs. If your first graph is at the beginning of the sequence, and the second graph is the end of the sequence, then small intersection no longer survives. It's only the large intersections, small distance no longer survives, and only large distances exist. So let me do the same thing pictorially, because I suspect that this is a little too much to parse, so let me explain by the same picture size. So we have now a collection of graphs, random graphs, going from 1 and then all the way to the independent graph. We take, for example, we take a largest independent set, we take an independent set of certain size in the first graph, and take another independent set in another graph somewhere in between. And we'll look at their intersection, and we ask what kind of intersection we can get. We can get large intersection, we can get small intersection, we cannot get intersection in between, So this is what we had earlier. This is the same picture. But however, now, if this second independent set is in the last graph, then high intersection is also no longer available. So what happens, the high intersections, they exist for a certain period of time, and then boom, they disappear. Let me maybe give you another sort of on the board, another picture of this. So as you do the sort of interpolation, and vertically, you plot the overlaps. So I'll explain what it is. So for each intermediate point T, you say vertically what points, what cardinality of intersection I can get. Turns out that it can be either small or it's large. And there are two curves, they look like this. So what happens is that until a certain point, small intersection and large intersection exist, but after a certain point, critical point, only small intersections survive and large intersections disappear. And certainly that applies to the endpoint graph. All right, so let me pause here, see if you have any questions. So should I? Okay, so you might not have it shouldn't be clear why we care about something like this, but questions, yes? Of course. Slide on the statement here?
Yeah.
Yes.
Okay, so well, in the end, does 2.2n or no?
They are.
If s equals 0, then Bij.
Oh, good catch. Yeah, you're really paying attention. That's a typo. It should be 2 log n. There.
And then also, so you're saying for the 0 and n over 2 case, the distance can only be large between
Yes.
two independent sets.
Yes.
And is there no more subtle variation of that in large difference, which is not n choose 2? Like the distance
Yes.
only being able to be within a smaller range?
Uh,
Or like a different range?
I'm not sure I entirely followed your question, but certainly when I said t is equal to n choose 2, this is the end point here, but in fact this applies to the range of points.
Yeah.
Yes.
There's going to be a range of points.
Where
Maybe there'll be like depending on like the difference between the s and the t, maybe
That's right.
Okay.
That's right. So there is a t dependence here, and but there is two kinds of dependence. There is a, say, high intersection possibilities and range of small intersection possibilities. So there is two curves here. The point is that the high intersection possibility, which you can work out to the very great detail, but the high intersection possibility dies out before you get to the end. Turns out that's what we'll need. Yes, Miko?
That point where it dies out, that's understood?
Yeah, you can work it out by the first moment argument. It's some number, root 3 over root something. So I don't know. It's like, I don't have a very terrible good explanation what it is, but you can work it out. Okay, good. So let's continue. All right. So you're clearly paying attention, even finding typos. I appreciate that. Now, very quickly, I will go through a related model, which is sparse random graphs, where most of the things just go through almost without the end. It's just the ends. It's just the scaling is different. So in sparse random graphs, these are graphs on nodes where every edge is present with probability d over n, and then the optimal value, as well as where the onset of the overlap gap property, that becomes slightly different. First, the optimal value looks like this. It's a double limit kind of statement, but has a very clean statement due to Friis in 1990. Largest independent set is order n, and the correction factor is log d over d times 2. Okay? And if you go above this threshold of this size of the independent set, they exhibit the same type of what we, overlap gap property, which I call the ensemble. Ensemble because it applies to collection of graphs. And now this statement holds with modular exponentially small probability. That's because we're dealing with linear size independent set, but and so on. So other than that, morally, it's the same story, but on sparse graphs. OK. All right. And good. So now, with that said, I'm going to switch to a completely different model. I want to give you another model that demonstrates something similar, but any questions about sparse graphs? OK, looks good. All right, now we're going to change the gear, change gears. And
David, can I ask you
yes?
a question? I mean, the 1, is there a meaning to 1 over, well, to 1 plus 1 over square root of 2?
Is there, I'm sorry?
Is there a specific meaning? Can you attach a meaning to this?
It seems to be this. This is a threshold where, by expectation, this property holds. Other than that, I'm not sure I have any kind of a meaning. But for that matter, I'm not sure I have a meaning for factor 2 in front of log. Why is it factor 2? Because this is the way things work out. So I don't have a good answers for that. But now let me switch gears and talk about something seemingly completely different. This is a different kind of optimization problem that, and it actually emerges from the field of statistical physics and called ground states and spin glasses. But don't worry about physics part. It's completely self-contained model and rather simple to state. So what we have a tensor with IID Gaussian entries, standard Gaussian entries. So it's n or the p tensor. So when p is equal to 2, that would be a matrix, but it's a tensor in general. So we have this random tensor, and what we do is we hit it with a binary vector, plus minus 1 to the n, so n-dimensional binary vector. We hit it in a linear sort of in a product way, and our goal is to maximize this objective function. So we maximize over all choices of binary vectors and want to make this quantity as large as possible. That's the optimization problem. So, and it's an algorithmic question. So yeah, just like the previous problem is algorithmic. I give you a tensor, you need to come up with a good vector that gives a good value. Okay? The scaling here is for convenience. You'll see why. And why is this scaling is irrelevant is because this problem has a global optimum, which is some constant called eta, denoted by eta of p. The importance of this constant and knowing what the value of this constant is hard to overemphasize. This is a constant that was predicted by Parigi in 1980 in using physics heuristics called replica symmetry breaking, and then later was confirmed by Talleyrand mathematically in 2006. And one of them got a Nobel Prize in physics, one of them got the Abel Prize in mathematics. So you can say that this fact is worthy of 2 major prizes. Right? Because in both cases, the replica symmetry breaking physically and mathematically was a key thing and cited in the citations of these 2 prizes. So this is a serious deal, as you can imagine. What we're going to talk about is algorithmically. How can we achieve this value algorithmically and so on? Turns out that this model also exhibits the gap of the similar kind that I've described for independent sets, in the sense that near optimal solutions are either close to each other or far from each other when they are sufficiently close to optimality. But I'm not going to go give you more details about that and so on. So this is possible to prove. In fact, the proof for large enough p's, now we have a rather straightforward proof of that. OK. Why am I torturing you with this? Because all of these structures have a creative sort of fundamental barrier to algorithms, as I'm hopefully will convince you of, right? And this is first as a genesis, looking at the structures like this. Why did we start looking at the structures like this? Overlaps, large overlaps, small overlaps, and so on. All of this was inspired by the statistical physics and specifically physics of the spin glasses. And this is what the overlap structure of these random structures is what prompted Giorgio Parigi to develop his famous replica symmetry breaking, which is physics heuristics. And a big part of it was confirmed by Talleyrand, as I already said. So not only this formula was what the value of eta p was confirmed, but many other things along the way. All right. Good. So that's wraps up part 1. Now we're going to go to part 2 and part 3. Any questions so far? We're good? Okay. I'm not going to introduce now any new models. So hopefully, if you spend a lot of energy and calories on sort of absorbing the details of the first model is good enough. No more new models to be introduced, except for one algorithmic model. So save some of the calories for later. What do we know about these problems, right? I've introduced some structures, but algorithmically, what can we say about these problems? Well, here's what we know. The first problem of finding largest independent set is the sort of poorly kept, most embarrassing secret in the field of optimizing random structures. Yes, we know with high probability that largest independent set is 2 log n. In this graph, back to dense Erdős-Rényi graphs, largest independent set, as I said, is 2 log n. But the best algorithms give you only half of that. This was observed by Karp, who introduced the dumbest algorithm you can imagine for this problem. It's a very naive, greedy algorithm that sort of does this sequential selection, 1 by 1, gives you half optimality, and nobody was able to improve since then. And this is rather embarrassing because the algorithm is not very creative. It's fairly silly algorithm. But nobody was able to improve on that, so that's bad. Independent sets in in sparse graphs, same story with the same factor 1/2 gap. All right, so this factor 1/2 gap seems an evidential algorithmic hardness gap. So evidential in the sense that nobody is able to improve it, but it's not like we have a theory p not equal to np that to explain this gap. This is where we are as far as the independent sets is concerned in either dense or sparse graphs. We're good. All right. So as for spin glasses, the story here is a little more modern. The really strongest and best state-of-the-art algorithms for spin glasses emerged relatively recently. And they do achieve the value of some value that's strictly smaller than optimality, except for the case when p is equal to 2. In that case, you can get to optimality. But for general p is, to remind you, is the order of the tensor. It's one of the parameters of the model. In that case, you get to some value which is strictly smaller than optimality. And to spoil you sort of the surprise, this is the value above which the overlap gap property takes place. So it gets all the way up to overlap gap property, but not beyond that. And that's going to be a story about this model, and that's going to be a story about independent sets in sparse graphs as well, which at this point might seem suspicious because overlap gap property happens at the 1 + 1 over √2, whereas algorithmic gap happens at just 1. So there is still a gap between the two that I need to explain further. Okay. We want to now argue a sort of main thesis of this entire thing is that presence of the OGP, the presence of the overlap gap property, is a barrier to algorithms. When we talk about algorithms, we need to discuss what's the class of algorithms that we want to consider, because algorithmic hardness is in relevance to some classes of algorithms. It would be ideal if this was class P, class of all polynomial time algorithms. But that would be proving p not equal to np, even stronger version of that. So that would be too ambitious. Let's not do that. We're going to restrict the class of algorithms. Historically, sort of this was done in the context of the so-called sort of what we call, for the lack of a better word, stable algorithms. But now I want to concretize it. So the class of algorithms that we will consider, at least for the purposes of this talk and the purposes of this work, is what is called in computer science low-depth Boolean circuits. And I didn't want to assume that you're familiar with this class of algorithms, so let me go over that. If this is something you've seen in the textbook of computer science, more power to you, that's great. So low-depth Boolean circuits. Jumping ahead, why this is going to be a right quote-unquote class of algorithms is that because all the successful algorithms, including the version of the greedy, including the algorithm for spin glasses, can be coded as a special case of this class of algorithms. So this is sufficiently rich, at least, to cover the successful algorithms. So, and then we're going to rule it out for the we're going to also rule it out above a certain proximity to optimality. Anyways, Boolean circuits. So, well, first of all, what's a graph? Graph should be sorry, not graph. What is an algorithm? An algorithm is a mechanism, a machine that turns input into solution, right? That's usually it's a Turing machine of some kind and so on. So this is going to be slightly different from Turing machine. But just to make sure that we get the input right, if it's a graph is the adjacency matrix on n choose 2 entries. So we're gonna model the input as a graph as just a Boolean vector of size n choose 2. And your machine, your algorithm needs to take it as an input and produce a solution like independent set. What is the independent set? It's an encoding of what's in and what's out, and that's a Boolean string of length n. Right? So any algorithm that produces an independent set given the graph as an input should be a mapping from Boolean cube of size n choose 2 to the Boolean cube of size n. This is kind of borderline trivial observation. And Boolean circuits are a particular structured class of mappings of this kind. So what are the Boolean circuits? They have more than two parameters, but two will be important to us. It's the size, which is the number of gates, and the depth, which is the length of the path, and it looks like this. So what we have here is that in the bottom part, we're going to input our graph. So it's going to be the graph is going to be fed here as a Boolean string. And in all intermediate stages, we have Boolean operations of the three canonical Boolean operations, and or a negation. These operations are connected, for example, in the first layer to some input points on the graph. So for example, this one is OR of 3 inputs, 1, 2, 3. And this is the negation of 1 input. And this is the end of 4 inputs. Once you populate the bottom level with some Boolean string, that propagates into level 1. And then it propagates to level 2 and propagates to level 3 and so on and so forth. So you keep propagating it until you get to level n, level Pn. The cardinality of the intermediate number of gates is varying. It could be larger than an input, could be smaller than an input, it could be all over. But as long as the bottom has exactly n choose 2 inputs, nodes, and the output has exactly n, then you have some structured algorithm to translate Boolean strings to Boolean strings. Okay? And your goal is to come up with a graph like this that solves the problem well. For example, on random graphs, it will produce large independent sets. That's the goal. To design an algorithm, in this case, means designing the graph like this, which is a Boolean circuit. And once again, there is 2 parameters here. One is the size, the number, which is the number of nodes in this graph, and the other one is depth, which is just the length of the longest path from the bottom to the top. Any questions about Boolean circuits? Okay. All right. So no time to give a sort of proper background on Boolean circuits. This is a huge, huge topic in theoretical computer science. I'm not going to do justice to that. Just mention a few things which are relevant to us. If you don't care about the bound on the depth, but only look at the size, as long as the number of gates in your circuit is polynomial, you have a polynomial time algorithm. So fair game would be polynomial time Boolean circuits. That's the thing. But we're going to bound it at depth as well. There's a bit of a literature on this, including studying the independent sets and cliques and so on. But the relevant to us part is that the algorithms that are the state-of-the-art algorithm for independent sets and sparse graphs or spin glasses can be coded as a special case of the Boolean circuits as I mentioned. Right? That is not immediately, so you need to do some intermediate steps and localize in the greedy algorithm for independent sets, but that's a kind of different discussion. Let me not go into that. In summary, if the algorithms that we want to understand the power or limits of would be circuits, Boolean circuits, which look like this, which will be bound at constant depth and well, in general, would be sort of controlled depth, but the polynomial size. Okay. All right. I'm going to share. Right. So this is a special case. It's good. Boolean circuits with some controlled depth and size in combination exhibit a certain fundamental property which is summarized in the so-called linear Mansur-Nissan theorem. And this property means that this class of algorithms exhibits a form of stability. I'm unloading a lot on you, so I'm going to take it step by step. So here's the formal statement of the theorem that you can find in textbook, linear Mansur-Nissan theorem. It says, so this is a formal statement. Let me give you a semi-formal implication. It says the following. Take the following quantity, d sub n. This is a logarithm of the size to the power, which is the depth. So for example, if the graph, if the circuit has polynomial size and constant depth, that would be log n to power 3, for example. It's a certain quantity. I will call it d sub n. What's the importance of this quantity? Informally, it means that whatever the Boolean circuit produces can be coded, written down as a polynomial with degree at most d sub n. Formally, that can be is stated in terms of the associated Fourier coefficients and the Fourier expansion of that. To make sense of this part, you need to be familiar with Fourier theory on discrete Fourier analysis on a Boolean cube, which is a fascinating subject on its own and so on. But I don't want to anticipate, expect the knowledge of that from the audience. Just think of it as the ability to write what Boolean circuit produces as a low degree polynomial with a degree controlled by this quantity, dm. Yes.
The size and the graphical model of the circuit is the total number of nodes?
Yes, the size is just the total number of nodes. Yes. And depth is the kind of number of levels. Good. Good. So for example, if the depth, as I said, so the depth is constant and size is polynomial, then you can write what circuit produces as polynomial, multivariate polynomial with degree at most log n to some power. And that's a non-trivial result because you can write any Boolean function as a polynomial, but in general it would require degree n, which corresponds to the number of variables, n choose 2 in our case. Good. Other questions? Yes?
Just one question. So when you say the small Fourier weight on the large stuff, or on the small
Yes.
stuff, I'm trying to work out what you're saying on the small layers, or on the, you know what I mean? So the statement, you're saying on certain layers,
Yes.
there's little weight.
Yes.
You're saying on the big layers.
Okay, sum of the, let me see, maybe there's the sum of squared Fourier coefficient associated with monomials of order, order at least, I should have said. Okay, good. Another type. Thank you for that. Yeah, another the clarification is needed. Of the order at least that. Good. All right, so, but here's the implication. Okay, low degree polynomial, so what? So what's the importance of that? The importance of that is that because it behaves like a low degree polynomial, sufficiently low, quote unquote, this class of functions is noise insensitive, or crudely speaking, stable. What does it mean? It means that if you apply this Boolean circuit to random input, like a random string, let's say uniform, or with some IID distribution, it could be a string as coding a graph, random graph, or something else. And now, let's say you resample one of the input, one of the coordinates. You just resample it and pass it through the algorithm again. So you have now 2 input. two outputs corresponding to the starting random string and one corresponding to the perturb random string where one of the coordinates possibly has changed. Stability means that these two output strings will be close to each other. They're not going to be too far. And you can control that with parameter d sub n. In other words, your algorithm, if you think of the Boolean circuit as an algorithm, that algorithm is stable upon changing the input of your input graph just by a little bit. It's not going to rearrange its solution too dramatically. It's going to produce roughly the same solution. If it was independent set like this, upon switching one of the edges, it's going to be slightly perturbed independent set. It's a stable algorithm, put it differently. All right? And that can be quantified, and it's quantified using this parameter d sub n. And I'll give you more precise statements. So now we're going to synthesize everything in the remaining 15 minutes or so, right? Okay. So we're going to synthesize. In fact, I might be even ahead of time. We'll see. The synthesis will be already kind of announced in several ways, but we're going to pitch, we're going to pit the property itself, the overlap gap property, against stability exhibited by Boolean circuits, and argue that, and by formal statement, that if you have an overlap gap property, then low-depth Boolean circuits cannot solve your problem. And that's where the buck stops as far as this class of algorithms is concerned. So put it differently, geometry conspires against algorithm in some ways that we will make precise. As it turns out, once your algorithm exhibits some form of stability, which is the case for Boolean circuits, these algorithms are doomed as far as the presence of the overlap gap property is. And the proof of that, I'm going to give you a pictorial proof of that, and it's a very simple proof. It's a continuity of one object versus discontinuity of another object. That's kind of a thing. And it's summarized in the following meta-theorem. I call it a meta-theorem or proto-theorem because every concrete instantiation of this theorem requires far more work and details and so on, including the Boolean circuit. So I wish I had a clean statement, sort of one statement that covers all the ground, but formal statement, but you can't do that. But informally, it goes as follows. Having an algorithm A, that means, again, it's a mapping from the inputs, like graphs, into solution bit strings, for example, coding independent sets. We call the algorithm stable if, as we said, a small change in the input results in a small change in the output of your algorithm. So changing a little bit your graph is not going to rearrange your independent set by the algorithm too dramatically. Okay? Then the claim is that in that case, algorithm cannot overcome the overlap gap barrier, especially the ensemble version of it, where we looked at the collection of correlated independent sets, correlated graphs. And here's the proof, and the proof is by picture. So let me explain the parts of this picture. So what I have here is a collection of, we have a collection of graphs, but what I plot here is a collection of algorithm applied to this graph. So you fix your algorithm, and then you apply it to this collection of graphs. And then you get some points in the Boolean cube. This is the first solution, second solution, third solution, fourth solution, and so on and so on. And you progress it until you get to the result of your algorithm applied to the last graph. Now, I want to recall the overlap gap property that we stated at the beginning of this talk. It says the following. We know that intersections between independent sets, they can be at most nu1. So distance can be at most nu1 or at least nu2, but cannot be in between. But we also said that if you look at the distance at the beginning graph, and for the beginning graph and end graph, that distance has to be at least nu2. So that picture. So in the beginning, it could be either here or here, but in the end, it has to be at most here. What does it mean? It means that when you apply your algorithm to the graph, you need to produce the points that stay with the distance nu1 to the first solution. So these distances, all of them has to be within nu1 from the first solution. But in the end, they have to be at least nu2 for the end point of the interpolation. And as a result, what it means is that at some point there was a jump over this kind of gap somewhere in between, where at some before the jump the distance was at most nu1, but after the jump the distance was at least nu2, because that's the only type of intersections that exist in these graphs with high probability. However, our collection of graphs themselves is continuous, discrete sense continuous. So only one edge at a time is being changed, right? So that's that by design, by construction. Furthermore, the algorithm is also continuous if one edge at a time change results in a small change in the solution. So that means that that path here is fairly continuous. To be quantified with little o's on, of course, all of this needs to be quantified, but qualitatively it's a continuous path, and continuous paths cannot jump this over this gap, which is linear size in the context of an independent set. And that's the kind of the contradiction argument one can build. Very simple idea. Any questions about the semi-formal or completely informal statement, or that's okay? All right, so good. So this is an idea, but now I need to make it somewhat more concrete. And really, to be honest, if you lose your attention at this point, that's perfectly fine. So the rest of this is going to be concretizing this with concrete deltas and epsilons and so on, so only to get it more precise statements. But if you don't get, if your sort of calories are gone by that point, that's perfectly fine. Okay, so here's a kind of a formal instantiation of what type of the lower bounds on circuits we can get with this methodology. Goes as follows. We fix a class of Boolean circuits. They have a size at most S sub n that we will say something about. This is number of gates in these Boolean circuits. They have a depth at most P sub n. So this is kind of upper bounds on the sizes. So this is a class of Boolean circuits with size at most Sn, depth at most Pn, and parameterized by alpha. And that means that this is a class of Boolean circuits that produce factor alpha optimum independent sets in graphs. So we want that it's a collection of Boolean circuits that needs to satisfy these three criteria. Solves the problem within alpha proximity to optimality and has this bound on size, this bound on depth. Here's a statement. Statement says that one of the two gives either the depth or the size, or both in some sense. So if the depth of the circuit is at most this number log n over log n, and I'll make a few side comments about why this is kind of very fundamental barrier. First, starting here. If alpha is larger than 1/2, 1/2, to remind you, is evidential algorithmic barrier for independent set. Nobody was able to. We can achieve 1/2. We cannot achieve better than that. So that's the right threshold. If alpha is at least 1/2, and the depth is at most that much, then the size needs to be at least this quantity, which is super polynomial. Details of the quantity is not important. The point is that it's super polynomial. So that algorithm is not polynomial time, and therefore it's not satisfying this criteria of polynomiality. Yes?
Is this any graph or a particular class of graphs?
It is. I'm sorry, I should have said. It does apply to sparse random graphs. So it is within the context of independent set in sparse random graphs. Right? As such, though, it applies broadly to graphs in general, and it says that if the Boolean circuits, if there's some class of graphs the Boolean circuits cannot do, it means that it cannot solve it for general graphs. We found out much later that for general graphs, these kind of statements can be inferred from earlier literature in circuit complexity. but not in the context of specifically sparse random graphs. So that there the result has a novelty. Okay, all right. So, okay. Here's the somewhat complementary statement, but of the similar spirit. Same alpha, proximity to optimality. There exists some parameter beta such that the following is the case. If the depth is at most some constant p, in other words, a constant depth, O1. If it's constant depth circuit, then the size has to be not only its polynomial size, it's nearly exponential size. So it has to be really huge as a result, and it's not polynomial time. This type of bounds actually is not very new. You see them if you go to the text on complexity theory of algorithms, you will find a similar type of bounds for something called the parity function. And this relates to this Hastad switching lemma and so on, so some development. So parity is a very simple problem to solve, but it's infamously hard for the Boolean circuits. It's kind of too sensitive, too unstable problem for the Boolean circuits to solve. So these type of bounds are not very new. What's new is that these bounds do appear in the context of solving random combinatorial optimization problems. Okay, right. So now the moral of the proof and why this works, I already mentioned. It's because Boolean circuits are stable, they are noise insensitive, but the sequence of optimal values or nearly optimal values is very unstable because of the OGP. So it seems like we more or less have a complete argument here. But there's some caveats that we had to unfortunately overcome, and I'll tell you that. All right, so the proof of these two statements goes as follows, just repeating what I sort of said earlier. We consider an interpolated sequence of random graphs, of sparse random graphs, because we want to argue about independent set in sparse random graphs. We take in a circuit. The circuit applied to a graph G sub t produces a solution. Independent set of I is denoted by I sub t. Okay, so we have now a sequence of solutions, sequence of independent set I sub t. What we want to argue is that this sequence of solutions is rather continuous. So, so we have something like, if this is your Boolean cube, 0, 1 to the n, then you get points like roughly continuous kind of a set of points, which presumably should be the case by application of the linear Mansur-Nissan theorem, which says that Boolean circuits are stable. The bummer is that that stability takes place, but on average. Linear Mansur-Nissan theorem tells you that for any fixed t, the likelihood that this change in your solution is going to be small it's true by expectation. Expected perturbation of your independent set is going to be small. But in expectation, that's not good enough for our purposes because we need to argue that the entire path is continuous. If it has some jump somewhere out there, then it's a fair game. There's no contradiction. So for that, we had to work a little harder and argue that, in fact, the entire path is continuous, but not with high probability. It actually is continuous with probability at least some exponentially small number, and this number is the degree of this implicit degree of the low-degree polynomials, the quantity that appeared earlier. It would be log n to the constant if it was polynomial size, low depth, and so on. So that by itself was that is something that required a special combinatorial argument and probabilistic argument to prove. I'll at the very end of the talk, I'll show you what's this kind of a standalone kind of result says. But assuming that's the case, then the rest of the picture works out. So just what we have is that with at least that exponential is, at least this probability, the whole path is continuous. If the algorithm is correct, then what must be the case that this event occurs at the event when the OGP doesn't take place. Because if it takes place and path is continuous, then the algorithm is not correct. So from that, you build the following inequality. The likelihood of this event, this likelihood should be smaller than this likelihood. This is the likelihood of not having OGP, which is exponentially small. And then the rest of it is just working out the parameters. So you plug in the d sub n. D sub n is log size to the depth. Depth is at most that much, so you obtain the lower bound on the size. And then by a very similar argument, you obtain the lower bound if this depth is constant, then you obtain this even stronger exponential bound on the size. All right, so the only sort of a standalone thing that we needed to prove is that this path is continuous throughout this so this stability occurs throughout the entire path. And that has to do with the following statement, which I guess it could be, in a way, an open problem contribution, which is a completely standalone question. It's nothing to do with algorithm, nothing to do with anything. But the following fact. Suppose, take a binary cube, 0, 1 to the n, and take any subset of edges. Edges in the binary cube where the edges is 2 nodes are continuous if there is Hamming distance 1. It's a very natural metric on this. And let little e be the density, the fraction of edges. And now consider a random walk, just a vanilla random walk on the binary cube that work continues for t steps. And you ask yourself, what is the likelihood that this random walk never hits the set of edges? And that can be bounded, lower bounded, with probability at least 2 to the negative length of the walk and the density of the set. That's something we proved. It surprisingly took us a little work. But it should, I'm somehow with thinking that should be some maybe simpler arguments. So if somebody comes up with like, I don't know, 1 page, half a page argument, that would be very nice. Maybe this is some implication of something else out there in the literature, but we couldn't do that. Good. Right. So if you offline, I can just repeat the statement and tell you. Turns out this very similar thing happens in the spin glasses. And up to the threshold, which is OGP, the algorithms succeed. Could be coded as Boolean circuits. And above that, they fail. And I'm going to wrap up a few things. Unfortunately, we could not do a similar meaningful statement for independent sets in dense graphs for Boolean circuits. The bummer was that the probability of OGP not taking place was too weak. It's exponential in the log squared n because this is the likelihoods of the clique sizes, independent sets. It's no longer exponentially small. It's a different scale. Something that we're hoping to do is to prove that OGP is a barrier to other classes of algorithms which have infamously unstable, like a Glauber dynamics or greedy type algorithms, other classes of algorithms for which the stability at least is not evident. So some work in progress that we're doing in this is with Fran Pernice in the audience and Ilya Zadik. Hopefully we'll get something out of it. And finally, is this a good theory? Is this the right theory for the algorithmic hardness in the average case context? We don't know. The evidence is towards that, but perhaps there's some interesting and meaningful and reasonable models which are evidently hard, but for which do not exhibit OGP. So far, every problem where we encounter hardness in the average case, we managed to come up with a proof of the OGP of some kind. But it's not to say evidence of the absence is not the absence of the evidence, or the other way around. So, all right, so this is the end of my talk. I'll stop here.
Are there any questions?
Yes.
Thank you for the very nice talk. I have a question on your spin glass slide. Did I read that correctly, that this multi-ensemble overlap property is only for E?
That is right. Yes, so when P is even and at least 4. When P is equal to 2, it is conjectured that it doesn't take place. In fact, modulo this conjecture, Andrea Montanari built an algorithm that achieves near optimality. We can prove it for odd P, but for P sufficiently large, but P like 3 or 5 is, we believe it takes place, but we couldn't prove it. Peter?
Are there results on the independent set question in the regime between constant 1 and 1 plus 1 over root 2? Like, is there any hardness results?
Oh, I'm sorry, I misled you. Yes, all of this is pushed all the way to the half factor in the. So this 1 plus 1 over root 2, because it was only appearing because it's a 2 overlaps of two independent sets. By switching to the multi overlaps, you can push it all the way to the known algorithmic hardness. So within factor half, you have a greedy algorithm. Beyond that, it's OGP, and all of this applies. Sorry, I misled you. Yes?
Okay, you gave us the results that said if, the depth is bounded or, constant, then we get the size has to be so large.
Yes.
Can we translate that into the degree of the polynomial approximation? What does that tell us about the degree? Because that was like log n to the
Yeah.
p or something.
Right. So, good. So to paraphrase the question. So suppose we know that for the circuits, if the depth is the most constant, the size of the circuits is at least exponential n to the something. The question is that can we say something like any polynomial that solves this problem, which has the constant degree, has to be a size at least exponentially large in this. I'm tempted to say yes, but I'm not sure that might require some work, because the translation from circuits to polynomials and vice versa is not sort of one-to-one. It's a little more subtle. But that's a great question. I have to think about it. Good. Yes?
You've talked about things that, like, basically trying to get something out of the noise. But have you thought about, like, blended structures? So a little bit about the spike tensor metal and
Yeah.
the glasses thing,
Yeah.
or blended clique
Yes.
and the other problems. Do you think some things that you've done?
Yeah. This is. I wish you didn't ask this question. There is no, that's fair game. So the reason, the answer is partially yes. So blended structures do exhibit overlap gap property of some kind. We can formalize it, and there's in cliques, in planted cliques, in linear regression models, which is a version of a planted model, and the others. The problem is that the class of algorithms that we can rule out with the structure is shamefully limited. So we can rule out with that rapid mixing of the Markov chain. So we can rule out that if you try to solve your problem by constructing Markov chain Monte Carlo method, it's not going to mix fast, and so. But that's pretty much the only class of algorithms we can rule out. It's nowhere near Boolean circuits and things like that. So that's the problem in our minds quite a bit. We just don't have a way. And offline, I can explain what breaks down in the planted structure, but it is. I joke. It's a great question. It's the one that keeps us awake at night.
Any more questions? So if not, let's thank our speaker again.